Thank you to Brilliant for supporting PBS. Black holes are a paradox. They are paradoxical because they simultaneously must exist, but can't. And so they break physics as we know it. But many physicists will tell you that the best way to fix broken physics is with string. String theory, in fact. And the black holes of string theory, fuzzballs, are perhaps even weirder than the regular type. Einstein's general theory of relativity tells us that if the density of matter is sufficiently ridiculous, ultimate gravitational collapse is inevitable. Matter should contract to a single point of infinite density, the singularity, which is surrounded by a surface from which even light can't escape, the event horizon. And we see these black holes, or at least their incontrovertible evidence, in many places out there in the universe. But black holes are also impossible. At the central singularity, the known laws of physics break down. General relativity comes into irreconcilable conflict with quantum mechanics. There's our first paradox. And at the event horizon, another paradox arises. On the one hand, general relativity insists that no information from the matter that fell into the black hole should be observable on the surface, the so-called no-hair theorem, which says that the only properties that we can observe from outside a black hole are its mass, electric charge, and angular momentum. That's not very many bits of information. On the other hand, if we calculate the amount of information that goes into a black hole to build it up, we get a prodigiously large number, 10 to the power of 10 to the power of 77 bits for a black hole the mass of our Sun. Black holes should have an enormous number of so-called microstates, hidden configurations, and this translates to an enormous entropy. The formula for black hole entropy was discovered by Jacob Bekenstein, who incidentally also inspired the colourful phrasing that black holes have no hairs to describe the absence of observable microstates in a black hole, which on the surface seems to contradict his black hole entropy formula. Here's an analogy. We can describe the behaviour of the air in this room with very few numbers, its bulk motion, its pressure, temperature, etc. But these few numbers emerge from the motion of every air molecule, and to describe that, we'd need the positions and momenta of 10 to the power of 27-ish particles. So the air has a very high entropy and lots of information that is hidden under very few macroscopic properties. But in the case of the air, the hidden information still exists and is in principle still measurable. Not so in the black holes of general relativity. The no-hair theorem says that there's no information beyond charge, mass and spin that's observable above the event horizon. The information contributing to black hole entropy could be beneath the horizon, but if we add one more fact, we run into serious trouble. Black holes evaporate by emitting Hawking radiation. We talked about this previously, but the TLDW is that Hawking radiation should be completely random, and so leaks away the black hole's mass without any of the information that went into building the black hole. When the black hole eventually vanishes, so does its enormous information content, and that violates a very deep and fundamental law, the law of conservation of quantum information. This threat of erasure of quantum information in a hairless black hole is the black hole information paradox. So yeah, black holes seem to be paradoxes, and yet they definitely exist. But you know what doesn't exist? Actual paradoxes. When we see an apparent paradox in physics, it's really a clue pointing to a gap in our understanding. Solving the paradox can lead us to new knowledge. While we've covered these black hole paradoxes before, and have even hinted at possible solutions, we've never actually solved them. That's what we'll try to do today. Ultimately, the black hole paradoxes stem from the disagreement between quantum mechanics and general relativity. The impossibility of the central singularity is the most obvious place where we need a theory of quantum gravity. But this is also the problem at the event horizon. A theory of quantum gravity would have really helped Stephen Hawking in deriving his eponymous radiation, but such a theory didn't exist back then in the 70s and still doesn't. Instead, Hawking used a hack, something called the semi-classical approximation. He was able to describe the black hole using pure general relativity, but then analyze its effect on the surrounding quantum fields, which only worked if the gravity at the horizon was assumed to be relatively weak, in which case quantum gravity effects shouldn't play a part. But that assumption may be wrong. If gravity starts to get quantum even above the event horizon, then it may be possible to actually encode information on that surface in a way that saves that information from destruction as the black hole evaporates. And it turns out that our most advanced theory of quantum gravity can do this quite neatly. Black hole paradoxes may be solved by string theory. In string theory, black holes are not hairless at all. In fact, all of those strings make them positively fuzzy. And so we come to fuzzballs. Well, very nearly. First, a spot of string theory. We've covered this horrendously complex topic in detail before, so I'm only going to give you the crudest overview. In string theory, all elementary particles are oscillations in one-dimensional strands that themselves are embedded within complex many-dimensional spaces. String theory immediately solves the problem of the black hole singularity because instead of collapsing all of the black hole's mass to a single point, it gets distributed around the ring-like structure of these strings, lose that pesky infinite density, and we start making sense of physics again. It turns out that string theory can make sense of the black hole event horizon also. The first step towards this was in 1996, when Andrew Strominger and Kamran Vafa created a black hole using string theory. In theory space, not actually. Now, I'll come back to some of the details later. For now, just the result. These guys found a way to count the microstates on the horizon, the number of possible configurations of stringy structures, the 1D strings themselves, and higher dimensional structures called D-branes, and the number they found exactly agreed with the Bekenstein formula for black hole entropy. It was hard to believe that this was a mere coincidence. It seemed they'd stumbled on the mechanism by which information could be encoded on the event horizon. The infinitesimal strings and branes of string theory might be the analogue of molecules that store the entropy of our room full of air. I should add that Strominger and Vafa did this for the somewhat unrealistic case of a black hole horizon with 4 spatial dimensions. But it was a decisive step, and it gave us a compelling reason to think that string theory might explain where the microstates of black holes live. But in order to solve the information paradox, we still have to get that information out of the black hole as it evaporates. The breakthrough came quickly. A year after the Strominger-Vafa result, Samir Mathur at Ohio State dug into that model to see if it could reproduce properties of the black hole beyond the entropy. And it did, almost too well. For instance, the profile of the radiation emitted by the strings precisely matched that of traditional Hawking radiation. This was another stunning match to theory, and also a way for stringy black holes to leak out their information. It was looking pretty good, but I realise I haven't really told you what these stringy black holes look like, or how they form, or how structure can actually be supported on the event horizon. For that, we need to finally get to the idea of the fuzzball. First, a thing that's weird about even regular black holes. If you were to dial up the strength of gravity, black holes would get bigger. That's different to pretty much everything else in the universe, which are crunched down to smaller sizes if you increase the power of gravity. This property of black holes is actually quite hard to reproduce in theories of quantum gravity. But while he was exploring stringy black holes, Samir Mathur found that the strings that formed the black hole would increase in size as the strength of gravity increased. In fact, if you have a bunch of strings dense enough to form a black hole in general relativity, it wouldn't actually collapse. Rather, it would grow to produce an agglomerate of strings with the same radius as a classical black hole. If this is right, then black holes don't have an empty event horizon at all, but rather a real surface that looks like a tangled nightmare of strings and branes, like the hairball coughed up by some hyperdimensional quantum cat. A fuzzball. Just as the neutron star's gravitational field is so intense that atomic nuclei are crushed into a soup of neutrons, a star collapsing into a fuzzball will see its constituents crushed into a soup of elementary strings. The most amazing element of the fuzzball paradigm is the discovery that quantum gravity effects might not just be important at the center of the black hole, but instead may pile up to the horizon scale. The ability for strings to maintain structure in this extreme gravity comes down to an effect specific to string theory called fractionation. The tension of a string is inversely proportional to its length. Tight rubber bands are naturally small because they are difficult to stretch, and vice versa. But in string theory, when you merge a large number of strings, the tension of the resulting object is effectively smaller than for each individual string, proportional to the number of strings merged. That means by crushing an enormous number of strings together, the resulting monstrosity can be stretched to enormous scales. The normally Planck-length strings can therefore pile up into fuzzballs with sizes ranging from kilometers to light years. The resulting fuzzball doesn't have a local event horizon, in that there's no single surface of no return. But from a distance, fuzzballs would look like black holes. Light trying to escape would still be massively redshifted, sapped of energy by the gravitational field, rendering the object effectively black. It would still cause massive gravitational lensing, time dilation, etc. All classical effects of black holes from general relativity would be preserved. But if you approach the fuzzball, you start to see this surface of stringy material with a thickness of about a Planck length. And what happens if you try to punch through that surface? Well, that's where things get properly weird. In fact, there is no interior. A fuzzball is really a fuzz sphere or a fuzz shell. It's not that the interior is empty, but rather that space and time literally end at the surface. As the fuzzball is forming, all of the matter, now dissolved into a stringy mess, is pushed up to the surface, and the interior grid of spacetime is deleted from the universe. This last thing is the weirdest and coolest thing about fuzzballs, so let's explore a bit further by dropping a few dimensions. Instead of the 4 spatial dimensions of a Strominger-Vafa fuzzball, or the 3 dimensions of irregular black holes, let's think about a 1D black hole. 1 dimension means a line, so a 1D black hole is just a segment of a line with a point of infinite density on it. The event horizon is just a pair of equidistant points on the line, inside of which escape is impossible. Now, let's try a string theoretic version. In string theory, we have extra compact dimensions, spatial dimensions that are coiled up on the Planck scale so we can't see them. Adding a single coil dimension to our 1D black hole turns our line into a drinking straw. The extra dimension is the distance around the straw. For a fuzzball, spacetime closes on itself at the event horizon. The extra compact dimensions contract and pinch off, so all spatial dimensions end in that direction. As a side benefit, this eliminates the problem of the gravitational singularity at the center of the black hole, because there is no central singularity, because there is no center. The emergence of fuzzballs in string theory radically changed our vision of what a black hole could be, and provided a satisfying potential resolution to several paradoxes. However, this picture is not yet complete. The model has only been carried out for simplified and non-realistic cases, like the Strominger-Vafa black hole. Constructing fuzzballs that more closely match real astrophysical black holes remains a major theoretical effort. I should also add that fuzzballs are not the only quantum extension of the GR black hole. We can come back to those another time. Black holes, or something like them, definitely exist, and they're one of our best hopes for understanding the union of general relativity with the quantum. Perhaps that'll come when we find evidence of fuzziness surrounding those distant holes in the fabric of spacetime. Thank you to Brilliant for supporting PBS. To understand astrophysics, Brilliant believes that it helps to have a solid understanding of relativity. Brilliant has a lesson on special relativity that includes interactive challenges and problems to solve. A hands-on approach can guide you through thinking strategies for challenging subjects like relativity. It starts out explaining relativity in terms of boats passing each other on a river, then goes into some puzzles that require challenging perspective, like the ball stack bounce, and then goes into the speed of light and even time travel. To learn more about Brilliant, go to brilliant.org/spacetime. Hey everyone, I would like to invite you to participate in the PBS Digital Studios annual audience survey. The Spacetime audience has always had a great showing on the annual survey, and we'd love for that to continue this year. Your feedback really helps us understand what you're interested in, and you even get to vote on potential new shows. And we really do spend quite a bit of time analysing and discussing the results. There's a link in the description below If you have a few minutes, we'd love your input. And as always, if you've joined us on Patreon, we can't emphasize enough how helpful your support is in keeping this show going. But today, on behalf of one of our generous contributors, we want to give a very special Big Bang shout out dedicated to the memory of Ernest H. Anderson Jr. Ernest was a geophysicist whose PhD examined Martian atmospheric haze, and he worked with the most famous planetary scientist of all, Carl Sagan. Ernest was also part of the Apollo 11 mission, working in the Air Force in Colorado tracking and predicting solar radiation bursts. We tend to talk about the famous scientists on this show, but it's the dedication, passion and hard work of scientists like Ernest that really carry the grand scientific project for all of humanity. So it is our honour to honour Ernest H. Anderson Jr., who passed away in 2018 and has returned to the stars. So we're going to take a short release break to take a breath and to get some mind-bending episodes written. We will return in December with said episodes and with the comment responses from the last episode, because we're also taking a comments break. See you all very soon.